Hello students, our topic for today's discussion is Lex and Yacc. You know that Lex is a lexical analyzer generator. That means this is the tool that is used to generate the lexical analyzer. Lex tool is used to generate the lexical analyzer in C language. The file which is provided as input to the Lex tool is written in this structure. You can see here. The first section is declaration section. That is written between these tags, like these tags, this one and this one. Then there is optional macro definition for regular expression. This is optional. That means we can define the macro for regular expression that will be used in rule section. This is the rule section. And the rule section is written like there is some rule, that means regular expression, then there is some action. After this, there is a subroutine section or user code section. Subroutine section or user code section. Overview of Lex. When this is the Lex source program, which is provided as input to the Lex tool. It provides lex.yy.c file. This lex.yy.c file is given as input to the C compiler. It provides the executable file as a.out. When we run this a.out and providing some input, it provides the token to us. In this figure, basically, this is the lexical analyzer which is written in C. That means when we want to use the Lex tool, we want to generate this file lex.yy.c. This is the lexical analyzer, and the executable for this lexical analyzer in this case is a.out. Now, first we will write the command as lex. Suppose that the name of the file is input file, and the extension for lex file is .l. So in the command will be lex input file.l. Then we will write the command C compiler lex.yy.c. That means we have to compile the file lex.yy.c. Then we will execute ./a.out file, and when we provide the input, it provides the tokens. Yacc file structure. Yacc stands for yet another compiler. Basically, Yacc is a parser generator. It generates the parser corresponding the given grammar as input. Yacc generates LLR parsing table. And the file structure that is given as input into the Yacc is like this. First one is definition, or it is also known as declaration section. When I am talking this is definition section, that means what? We are defining some functions here. Some functions here. When I am just telling it as declaration section, that means what? We are declaring the function here and defining at last here. But in this case, in declaration or definition section, all the header files are included here. The variables that are declared here that can be used by basically the global variables are declared here. And then percentage token, that means we have to write this tag to just write what are the tokens that are used in this file. Percentage start signifies that which is the start symbol. Percentage left is used for left associativity. Percentage right is used for right associativity. That means what? If there is a operator plus and minus, and we want to show that plus and minus have the left associativity, in that case we have to write percentage left plus minus. Then there is a rule section. This is the rule section here. In this case we are writing the grammar and the semantic rules. And then there is a user code section or subroutine section. Now the purpose of this lecture is to understand how the code are written to communicate between Lex and Yacc. That means how to merge the code so that we are providing some tokens from the Lex that are taken as input to the parser, and parser uses the grammar to generate the abstract syntax tree or just parse the given statement. That is the purpose of this lecture. So the next file that I am talking here, how to write in the next PPT, I am just talking about how to write the Lex and Yacc program that will communicate with each other. First, we will give the Yacc source program as input to the YACC. This is not Lex, this is YACC here. YACC, it generates file y.tab.h, y.tab.c, y.output. These files can be generated when I am providing Yacc source program as input to the Yacc YACC. Here it is YACC, not Lex. Then y.tab.c, basically this is the parser. Because YACC is the parser generator, it generates the parser in C language. This is the parser y.tab.c. This y.tab.c and lex.yy.c. Lex.yy.c is what? The lexical analyzer which is generated by Lex tool. It is given as input to the C compiler. Then we are getting a.out. When we run this a.out, some input is given. It provides the parsed output. You can see what are the commands that are required here. First, we have to write yacc-d input file, the name of the file .y. We will get two files in this case. One is y.tab.h, another is y.tab.c. Basically in y.tab.h, some variables that are declared, global variables that are declared in the .y file, but that variables are used by the .l file. Those variables are declared or it just make simple to communicate between the Lex and Yacc. If some variable is declared in Yacc, it can be used in Lex also by using y.tab.h. Then there is another command yacc-v input file.y. When we just write this command yacc-v input file.y, it create a file y.output. This is the file where you can see the LLR parsing table. This is the file for just writing the LLR parsing table. Then when we are getting these files y.tab.c and y.tab.h and y.output, this y.cc, then we are writing the command as cc lex.y.c and y.tab.c. We are compiling those files and we want to get the executable file. When we run that executable file and providing some statement as input, it will provide you the parsed output corresponding that statement. That is the communication between Lex and Yacc. Now we want to just see how we are running the program, how the program can be run, but how we can run the program when the program is written in Lex and Yacc, and how we are establishing the communication between Lex and Yacc. For that purpose, you can use any Linux system, and I am just using here the virtual machine. In that virtual machine, basically you have to install two tools. One is Lex, another is YACC. When you are installing the tools, you can install the tools by using the techniques of or you can say that by using the commands that is used to install any tool in any package, or you can say the tool in Linux. Here I need two packages. One is Lex. For that purpose you can write the command sudo apt-get install Flex, or you can say Lex. Just run this command. This Flex, or you can say Lex, will be installed in your system. Then you have to install Yacc. I am just using here for parser generator, I am using the tool Yacc. Just write the command like this: sudo apt-get install Yacc. When do you install? When you have installed these packages, then we have to write the code for that means what we have to write two files. One is for one is .l file for lexical analyzer, and another is .y file for parser. For example, I have written here some code here. First, when we go to the this folder arithmetic expression, you can see here I have written two files, arithmetic.l and arithmetic.y. When you see that arithmetic.l, uh, arithmetic.l, in this file you can see here in the declaration section I have written hash include stdio.h because I am using here the printf statement. If it is not used, this is not required. You can just remove this. If it is I have written here hash include stdlib.h because I am using the function as atoi, text to integer, and I have included here hash include y.tab.h. This is the header file which is generated by .y file, and the variables that are defined here and there, that will just come, or you can say the functions that are defined there and here, it can be used in both files by using this header file y.tab.h. Now I am just writing here extend int yyl. This is the global variable. This variable basically there is a name. It is given here. Is the standard name yyl. This is the name in which if I am just getting any token in the lexical analysis phase, that token, for example, I am just taking the example here. We can understand good by using some example. I have written here the regular expression at 0 to 9 plus. It can match any number. If suppose that the number is 2, it will be matched here. That number will come to the YY text. It just convert ATY by using ATY. It just convert text to integer. That means 2 will be converted into integer. That integer value will come to the YYL value, and it will return the token as num. That means what? Here there are two things. The name of the token is num, and the attribute corresponding this token which I am sending, the value of that token, that is what? 2. This value is saved into yyl, and this is the variable which can be read by the parser at the time when the parser is getting num. When the parser is getting num token, it can read the value from this variable yyl. Now by default this is int, but we can change the type of this variable also by using the type of this variable yyl is yyS type. So that means what if I am just writing hash define yyS type float, then the type of this variable becomes float. Then I have declared a function here int ywrap, this one. The purpose of this function is what? When any file is given, or you can say any input is given as input to this file, when that file, when we are getting the end of that file or end of that input, then this function is called for wrapping purpose. When the end of that file is we are getting the end of that file, then this function is called and it return 1. If it return 1, it means what? We have got the end of the file. If it returns 0, that means the end of the file is not, we have not got any character corresponding end of the file. That is the purpose of ywrap. You can see here I have written the regular expression here and corresponding some action yyl, this one, and this one for the tab there is no action. For any other character written yy text 0. So here I am writing for every arithmetic expression. Suppose that the arithmetic expression is 2 plus 3 into 4. So what the tokens I am getting here? 2, that is integer. So this will be written from here. When I am getting plus, this will be matched here, and yy text 0 will be written. That means when I am getting plus, I will return the plus. When I am getting asterisk, I will return the asterisk in the character form, because this array is the character array. Now, this is our file of .l. Then we can say .y file, and I just want to see the .y file. It is like this one. This is the declaration or definition section. Hash include stdio.h because I have used the printf statement here, and void yy error character asterisk. This is the function which is used to print the character, or you can see which is used to print the error, and this is the function int yylex. It is used to just call the yylex. Sorry, it is used to just call the lex, but you can see here it is automatically called by this function yyparse. It call yylex, and there is a default definition of yylex. There is no need to write the definition of this yylex because there is a default definition of yylex. That is default definition of yylex can be used by this tool. And then there is percentage start symbol of this grammar is s, then percentage token name is num, which I have written by the .l file. Then left associative is plus, and then left associative is also asterisk. Then this is the grammar. S derives to e derives to e plus t. I have written here in single quote because plus is a character here. Then this is terminated here. Then e derives to t derives to t into f. This one t derives to f derives to num. Then I have written here the semantic rules. When I am writing here the semantic rules, if it is remembered to you, when I am writing the semantic rules for the arithmetic expression in syntax directed translation scheme, in that case, for this production f derives to num, we were writing like this: f.val equal to num.lexer. But here in YACC, pseudo symbols are used. The left side of the production is always $. This f is $. Then $1, first variable is $1, then second variable is $2, then third variable is $3, and like that. But num is a token here, so it is $1. So we can put $1 value into $. That's why it is written here $, equal to $1. Then the production is t raised to f. In this case, this is $, this is $1, so we have to put $, equal to $1. That means I'm just putting the value of f into t. Then this production, in this case, what was the semantic action when we are studying the text directed translation scheme? T.val equal to t1.val into f.val. So it is written in the same way. T.val, that is $, equal to, this is $1. This is $1 t $1, and if I am writing here $2 in place of asterisk, then it will be a character, not an operator. That's why I have written here asterisk only, because this is an operator here. And then this is $3. This becomes $1, $2, $3. Sorry, $1, $2, $3. Now in this case, $, equal to $1. Next time assigning the value of t, attribute of t into attribute of e. Now in this case, it rise to e plus t, $, equal to $1 plus $3, $, equal to $1 plus $3. This one. Now s derives to e. What we want to print? We want to just print the value of e. That is $1, $1. So I just written here printf the value is. Value of that expression 2 plus 3 into 4 is $1. Then in int main, I just called here yyparse. This is the function which is used to call the YACC. When we run these programs, the first function which is called is yyparse. It calls yylex, and when yylex is called, it returns the token from the by using the .l file. That token is taken as input to by this file, this .y file. It just put those tokens in the parse tree and construct, or you can say it construct the parse tree. And when any reduction is performed in the parse tree, or you can say it is evaluated from bottom to up, and in this way all the semantic actions are fired. When the semantic action is fired, the attribute value is calculated, and at last when we are getting the attribute value of the top node, or you can say the starting node, that becomes the value, attribute value of that expression, or you can say the value of that expression. Now we have written these files. How to run these files? Now for that purpose, first we have to write Lex arithmetic.l. It will create a file lex.yy.c. This is the file which is created after this command lex arithmetic.l, lex.yy.c, this one file. Next, we have to write yacc -d, and the file name is arithmetic.y. It will create two files. One is y.tab.c and another is y.tab.h, this one file. y.tab.h and one is y.tab.c. This is the parser and this is the header file which is used to communicate between two functions, or you can say two steps of compilation. Now after this we have to compile these files lex.yy.c and y.tab.c. When I have compiled this file, what I am getting here? A.out. When I run this file ./a.out, and if I provide any arithmetic expression according to the grammar, that is what 2 plus 3 into 4, and I press here Control D after this, what value I am getting here? 14. That is the value of this expression. 3 into 4 plus 2, that becomes 14. Now you can see here, in this case the parser is providing the value of that expression. Basically in YACC, if the grammar is as attributed, then YACC can also evaluate the expression. And we are using that facility. That's why I am just getting here the value of this expression as 14. Now when we run this expression and provide another value, suppose that I'm just providing 3 into 4 into 2, and we want to get the value, that becomes what? 24. So what we have to do? We have to just write dots, run this executable file and give the input. Suppose that the input is this, and press the enter and then press Ctrl D. You will get the answer. Now another, you can see this is the one example for arithmetic expression, but if you want to see more examples for that purpose, you can see here I have written here another example, count binary 0. Count binary 0. So you can see you have to go this directory and there are files .l, and we have to write this one gedit and bin0.l. You can see here this is the .l file. When I am providing binary number as input here, there are two input, one is 0, another is 1. So I have written here one token as 0, another token as 1. For other things, just we don't have to consider those things, and all the other things are same as we had discussed in the previous example. Now when you see .y file corresponding this .y file, and come to this one file, you can see here all the things are same, only I have just changed this grammar and this semantic rules. You can see here this is the grammar as raised to n raised to nd, n raised to d raised to 0, d raised to 1, and we want to count the number of zeros, as when we are discussing the syntax directed translation scheme, at that moment we had discussed the SDT to count the number of zeros in a binary number, and these rules are written according to that only. When I am getting d raised to 1, that means $$ equal to 0. We don't have to count because this is 1. If I am writing d raised to 0, in that case $$ equal to 1, n raised to d $$ equal to $1, n raised to nd $$ equal to $1 plus $2 semicolon, and this one printf $1. We want to print the number of 0. Here the tokens are 0 and 1, and the start symbol is S. And other things are same. When we just want to execute this program and when we want to just establish the communication between Lex and Yacc, so for that purpose, first command we have to write Lex bin 0.l. It will provide you lex.yy.c, and after this I have to write yacc-d, and the file name is bin 0.y, the Yacc file, and it will provide you lex.y.type.c. Then we have to compile lex.yy.c and y.tab.c. It will provide you the executable. When we just run that executable, a.out, and I'm just providing any binary number as input. Suppose that this is the binary number and we want to count the number of zeros. In that case, we have to just put here control D. The value is 2. Number of zeros that present in this expression is what? 2. So it prints 2 here. When I provide another input, suppose that the input is 0001. How many zeros are here? 5. That means if it provides the 5, it is the right answer. The value is 5. So this program is used to count the number of zeros in a binary number. Another program which I have considered here is what? Just convert how to convert the binary to number into decimal number. And we want to see that, so we have to go to the binary to decimal, this, and I written here already. I have written here the program. You can see here gedit and bin to deck.l, and you can see here the .l file will be same because I am just taking the input as binary number. What are the tokens that are present in binary number that are same as the previous example. So we want to just see the .y file. This is the .y file. You can see here I just changed this one. Grammar is also same because we were talking in the last question about the binary numbers. So in that case the grammar is same, only the semantic rules are changed. What are the change in the semantic rule? You can see here. If I am getting d raised to 1, $$ equal to 1, it becomes 1 here now. It becomes 0. And when I am getting this production, it becomes $$ equal to 2 into $1 plus $2. Okay, yeah. That means what? Basically, this is what? This is just like that. When I'm writing n raised to nd, in the when we were discussed the syntax directed translation scheme, at that moment we have written the semantic action as what? N dot val equal to this one n dot val, n1 dot val into 2 plus d dot val. This is written in the same way. This is $. This one is $1 into 2 plus this is what? $2. $1, $2. D is $2 here. $1, this one multiplied by 2 plus $2 is what? D. And here what I am getting here, the value of n, the printf, the value is this one, and that is what? I am just printing here $1. That will just give the decimal number corresponding the given binary number as input. When we want to see the output of this, we have to write first lex bin to deck.l. It will provide you the lex.yy.c. Then we have to write another, you can see here, then we have to write yacc hyphen d and our Yacc file bin deck.y. It will provide you y.type.c and y.type.h. Then we have to compile lex.yy.c and y.tab.c. When I just compile this, I will get the executable. You can see the executable, that is what a.out here, the ./a.out, and I just execute that and provide any binary number as input. and we have to get, and just press Ctrl D, we will get the corresponding decimal number. You can see here the decimal number is 13. That is what same as this one, 1 2 4 8, that is 12 plus 13. And when you want to see another example, for example you are providing 100, it will be what, Control D, it is 4.